Hello and welcome to Lesson 33, Implicit Differentiation. This is the I think we're getting into more challenging types of differentiation at this point in time. So today what I want you to be able to do is, again, you need to identify when it's necessary to use this rule, and then I want you to be able to successfully determine the derivative. So those are your two overlying goals here: identifying when to use it and successfully determine how to use it. So sometimes functions aren't in the right form. So sometimes they're not in the y equals or f of x equals form. So in this, sometimes it's easier just to take the derivative as is instead of rearranging. So for example, if I gave you a function that looked like this, xy plus y squared equals 2x, and I said take the derivative, and you're going to look at this and say, well, I need it in the y equals. How do I get it in y equals? And a lot of you will be saying, that's a little trickier than it looks. And the answer is, or can you do it? Of course you can, but it would be nice if we just take the derivative as is right there and not have to worry about rearranging it. And that's what I'm going to show you today, how to take derivatives without rearranging equations. So much quicker. So, quick recall here. Remember that f prime of x is our derivative notation. That's the same as saying y prime. And earlier I said Leibniz notation. We're going to come back to using it, and it's dy by dx. So all three of those are they mean the exact same thing. Okay, they mean the exact same thing. And when I say dy by dx, and this is why Leibniz notation, I kind of like it, especially when we get into word problems, it means we're looking at the change in x with respect to y. All right, and that's just slope. You're sitting there thinking, well, that's the definition of slope. Exactly. Remember, this, when we're taking derivatives, we are just looking for an expression of slope. All right, I can't stress that enough. So that being said, Leibniz notation is nice because it reminds us of what we're looking at, dy by dx, the change in x with respect to y. All right, so here we go. If I gave you this, 3x squared plus 2x d by dx. So what does that tell you? And I'll write this out in words in a sec here. It means here's the function, and here's the instructions. And that instruction is take the derivative of what's in the brackets. So take the derivative of what is inside brackets. So it's the way Leibniz says take the derivative of this. And that's that d by dx, that's the indicator. And it says take the derivative with respect to x. All right, so here's a quick example for us, and I'm going to do it out in slow-mo here. And if you have any questions with this and clarify it when we come together and see each other, I'm going to throw a non-x variable in here. So Leibniz notation, it says we're going to take the derivative of what's inside the brackets with respect to x. So we're taking the derivative with respect to x. So that means that when you're taking the derivative of x, so the first term, it becomes 6x, its exponent comes down, and you need to indicate, hey, I took the derivative of x with respect to x plus the derivative of 2y. You would just take the derivative as normal, so y to the 1, so that would become just 2, and I took the derivative of that variable, dy by dx, with respect to x. All right, now, as we said before, up here, the change, get some magic pen going here, this is just the change in x with respect to y. Well, this would be the change in x with respect to x. That's a one-to-one relationship. So no matter how x changes and y changes, it's just going to be a one-to-one relationship. So we end up with 6x plus, on this side though, this is 2 times how x changes with respect to y. We don't know that information, so it just remains as is. So dy by dx. And that's your derivative. your derivative can have some of our notation from Leibniz or Newton, depending what method you're going to use, okay, in its final answer. If you're going to be a Newton calculus student, it's going to look like this, 2y prime, because dy by dx is the exact same as y prime. All right? So it doesn't matter, and I flip-flop back and forth. It's more convenience for me. All right? So let's take a look here. Differentiate where possible. So how do we take the derivative of this? Remember, you need to use all your previous rules. They haven't disappeared. I have x times y. That's going to be product rule. And then just straight power and a constant. So product rule says take the derivative of the first function. So the derivative of x is 1. And I'm going to go dx by dx multiplied by the second function, y, plus the first function multiplied by the derivative of the second function. And the derivative of y is the same as derivative of x. It's going to result in a 1. And I took the derivative of y with respect to x equals the derivative of y is 1, and I took the derivative with respect to x, and then I'm going to put the 0 in just for form, or just to show you off the start here. Now, if I go back, we said the rate of x changing with respect to x is always going to be 1, and of course we'd never write the 0 in anyway. So what does this look like when you clean it up? Y plus x dy by dx equals dy by dx. There we are. Now I'm going to simplify for dy by dx because there's some questions in the homework that want you to isolate for it. So that means I'm going to subtract the x dy by dx from both sides. And remember that dy by dx, it's a value. Okay, it's a variable at this point in time. And you treat it as such. So dy by dx, and we'll common factor it out, 1 minus x, because it represents the slope of the tangent line. So that means that y divided by 1 minus x is equal to dy by dx. So there is slope. This is the expression of slope. The difference is that you not only before, when we were calculating slope, you just had to know x. Now you have to know y and x, which means you need the whole coordinate when we're looking at a point on the curve. All right. So this one I'm going to use with y prime to show you, if you're Newtonians, what it looks like. So again, quickly looking through, power rule. Now that's product. That's a constant, so no problems. So derivative of 3x squared is 6x. I'm not going to put the dx by dx in because dx by dx is always 1, and you haven't had to do dx by dx up to before, so why do it? Start doing it now. So that first term just becomes 6x minus square brackets, because we got a negative sign to distribute here. Product rule. Product rule is derivative of the first. The derivative of x would be 1 multiplied by the second function minus the first function multiplied by the derivative of the second. So it'd be 2y. And now I have to indicate I took the derivative of y with respect to x with something other than y. So now instead of dy by dx, you can use y prime. Really up to you as to which one you choose. And the derivative of 6 is 0. Now I'm going to get rid of brackets. So 6x minus y squared minus 2xy y prime. Now the only reason sometimes I prefer not to use the y prime is because if you get like me, you get a little silly with your pen here, and sometimes you forget the y prime and so on and so forth. So dy by dx kind of forces you to remember. I'm going to solve for y prime. So I'm going to move that term to the other side. So 6x minus y squared equals 2xy y prime. I want to find the slope, so I'm going to divide by 2xy. So y prime, the slope of the tangent line, is simply going to equal this. There we go. Final answer. And again, the only difference is there's x and y's in your final answer, so that means you need to know the entire coordinate if you want to actually find the slope for that expression. All right. And an example here. Last one, determine the equation of the tangent line. All right, so I just want to do an example because this one's a little bit different. The other ones, once you get the hang of how to take the derivative, they're fairly straightforward. This one's a little bit more challenging. So First thing I'm going to do is I'm going to rewrite everything in exponential form. So x, y, and this one kind of has pretty much kitchen sink, you can think of it. Okay, because I got power rule, so we can handle that. Now this is actually our chain rule. So a little bit different, chain rule, and we got back to a power, so that's no problem. So let's start off. Derivative of y to the 1/2. It's 1/2 y to the exponent negative 1/2, and I'll go with y prime. I'll just have to be careful with my primes. So I took the derivative of y, and when I took the derivative of y, I indicated that I did also, that it wasn't with respect to y, so that's why the y prime's there. Equals. Next one, chain rule. 1/2 bracket xy to the exponent negative 1/2. So there is my, and again, you probably don't want to do this with your note, but stripping the onion or peeling the onion. Now I have to multiply by the product rule. Derivative of x is 1 times y plus derivative of the second function would be 1 y prime minus the half would come down, so I'd have 2 1/2 x to the negative 1/2. So there we go. That's what it looks like. So I'm going to do a little bit of cleaning up because here I have to distribute this in. All right, and I want to get rid of, you can go back to radicals. So in this case I will. With the exponent of negative 1/2, that's 1 over root y, and then the 2 from the 1/2 will be down there. So the y to the negative 1/2 is simply negative exponent, means you flip it to the denominator. 1/2 is a square root, and that's multiplied by y prime, equals, so this expression is going to be 1 over 2 root xy, and I have to multiply it into y plus xy prime, minus the 2 and the 1/2 cancel out for us, and it'll be 1 over root x. So I have to get all the y primes to the same side. So the first thing I need to do is I need to distribute and get rid of that bracket. So I end up with y over 2 root xy plus xy prime over 2 root xy minus 1 over root x. And some of you are thinking, whoa, this is a little on the ugly side, and you're right, it is, but it's manageable. So I need to get I need to get the y primes all to the same side. So I'm going to subtract that term to move it to the left side. Y prime minus xy prime over 2 root xy equals y over 2 root xy minus 1 over root x. I'm going to common factor out the y prime. So I have 1 over 2 root y minus x over 2 root xy. And this mess again. Now you can get a common denominator. It's not necessary. If you want to go ahead and do it, you can, but you'll find that you can do the calculation because all we're going to do is a simple substitution in here in a sec. So there we go. So that is what the slope of the tangent line to that curve looks like. All right. Now, how are we doing here? Okay, so when I look at the original question, we want to look at it at x equals 4, but I need to find y. So I need to go back to the original function, root y equals root xy minus 2 root x, and I need to substitute and fill it in. So I'm going to cheat a little bit here. I'm going to pause it and solve. Okay, and you can see here I substituted 4 in to the equation. So I took 4, I substituted it into this equation. So you can see it in this line here. And from this point on, I just solved for my y term. Now I'll pause it. I'm going to calculate final slope for you, just so you have it all in one video. Okay, so I've taken the equation of slope from the other side that we determined right here. Okay. And I've moved it over here, and I'm substituting in the point that I have. Point is 416, so now I'm just going to simplify, and everything's perfect squares. So after doing the calculations, I found that the slope is positive 4. And in my final statement, I found the equation of the tangent line. There's the assigned homework. If you have any questions, let me know.